Hi everyone, my name is Mitchell Rice, and I'm in Dr. Hassan Rashidi's Design and Manufacturing course this fall at Georgia Tech. This is Project 2, and in this project, I was challenged with the goal of improving a product that I commonly use and using design for X qualities, improve the product and its ease of use, its human factors, and ergonomics. Now, I'd like to ask you before we begin, no matter where you work, what you do, if you're a student athlete, if you're in industry, are there some things that get on your nerves in your everyday work? Well, I can tell you for me, as an engineering student here at Georgia Tech, something that gets on my nerves is having a messy work setup. You know, having a messy work setup really hinders my productivity, my performance, and also my happiness when I'm working on homework or a project. Now, you might do many things to clean up your setup, whether that's vacuuming your floor, cleaning off your workspace with a sponge, or leaving it as it is, as shown in the top left. You know, for this project, the product that I wanted to improve upon was a compressed air can. Now, a compressed air can is commonly used to clean electronics, clean a workspace, or even clean internal parts of an electronic device. Now, as we move into improving this product, I would like to introduce a concept known as mass continuity that's studied in fluid mechanics. There on the right, you can see the fluid mechanics equations, and I'd like to discuss these a little bit. So shown in the bottom left is a picture of a nozzle, and a nozzle is a good representation of the fluid mechanics mass continuity equation because it takes an inlet of air and then sends it through a nozzle into the outlet. Now, as you can see on the right, the mass continuity between inlet and outlet are equal. This depends on the density of the fluid, the cross-sectional area of where it flows, and the velocity as it flows through that area. Now, in the case of a nozzle that we might be blowing through, the density of the air would remain constant, so that can be canceled. Now, specifically, we're looking for the speed of the outlet, where the air will actually come out and clean our surfaces or our electronics. So after rearranging this equation, we get that final equation shown in the bottom of the relevant equations box. And you can see that as the area decreases going towards the outlet, the speed will increase, driving a higher speed of air towards the electronics to clean out dust and other artifacts that might be causing your products to get you sick, not function as well, or just make you uncomfortable in your daily work. Now, you've seen something similar to a funnel or a nozzle in many different cases, such as the shower nozzle in the top left. As the water comes through small holes in the shower head, the water speeds up and keeps a fluid flow down towards you. Now, in the middle, that's a carburetor that's part of an engine, and it uses nozzles to drive fluid through the engine. There in the bottom left, a common fun item, a jacuzzi. You can see that the water speeds up as it comes through a nozzle and pressurizes towards the person in the jacuzzi. And then even a jet engine nozzle, shown in the top right. This really provides the power behind a jet as it flies through the air. Now, as we move into my product that I would like to improve upon compared to the compressed air can, I'd like to show that to you now. I've named it the Puff Duster. It's an affordable, effective, and reliable replacement to a compressed air can. Now, some of the features that I'd like to point out, it blows its high velocity through the top outlet nozzle. There's two stable grips on the outsides where, as shown in the video here, you can hold on either side while blowing through the nozzle to clean off your electronics. And then also I included some fins on the sides too when designing to give it a more aesthetic design when it's sitting on your desk, almost to look like an aerospace product or part that they might produce, such as a rocket. Now, I'd like to also move into some specifics on how this device operates. So there's a couple important facts on the left. Air velocity around 20 meters per second is required to blow away particles that might get in your workspace. And a human can blow on average about 10 meters per second without straining their muscles as they blow. Now, the nozzle mechanism of this device that I've specifically designed greatly increases the velocity as the air goes through the nozzle, and it cleans the workspaces as the air is centered towards the dusty areas. Now, there in the left picture on the top, you can see the inlet of my product. It has an outer diameter of 0.85 inches, and you're seeing the bottom view there. Now on the top right, that's the top outlet part of the nozzle. Its inner diameter is listed as 0.1095 inches, and you're seeing the top view. Now after running these calculations and comparing the two areas and multiplying that times the inlet velocity of an average of 10 meters per second, we see a great increase in the output velocity with this product. Not even accounting for pressurized air such as in a compressed air can. But I would also like to point out this is not accounting for losses due to friction that might be very realistic in this case, which might be the result of seeing a much larger velocity of air coming out of the outlet. Now moving on, I'd like to show you the live prototypes that I got out of a result after I 3D printed. There on the right, you can see the 3 different sizes that I printed from the left to the right, increasing the outlet nozzle size. Now these different sizes are meant for different purposes in cleaning your workspace. There on the right, the purple one could be used for large applications, such as cleaning off the surface of your desk. Now the yellow one, the middle diameter size, could be used for more specific cases, such as cleaning out your keyboard, or even a couple small nooks in your office setup or around your house. And then the smallest setup, the blue one, has a very small nozzle. It is meant for very specific situations, such as cleaning out parts of your phone, or even cleaning out small parts of your laptop keyboard. There on the left, you can see a video of me actively cleaning out my keyboard as well. Now with this product, it's very important to point out the different design for X capabilities. Well, specifically the puff duster designs for reliability. Compared to a compressed air can that gives out within a couple weeks or a month, this puff duster can be used time over time without needing to replace it. It also designs for cost. The consumers can easily 3D print these parts much cheaper than a $5 to $10 compressed air can to clean their office and workspaces affordably. And also it designs for safety. Compared to a compressed air can, this product is not flammable or explosive compared to a can. It's also meant to be printed out of PLA, which I'll get into it here in this next slide, because PLA is specifically safe as it's made out of cornstarches and other simple digestive plastics. The dust puffer will be made out of either PLA or PETG, as I said, also because it's cheap. It costs around 5 cents to 15 cents per gram. And as I said, it being manufactured, it could be manufactured with 3D printers, industrial or consumer 3D printers, to make it accessible to all. Now these can be produced in about an hour and a half, and in total they take about 18 grams of filament, which comes right under $1 in total to make. Now here in my conclusion, I've listed my sources on the engineering work I've done, and also some pictures here in the slideshow presentation. I would like to point out that this video was meant for educational purposes only, and patent research was not considered. Thank you.